Everyone, introduce. My name is Sihotang. With name 5233530 and 2. I am a student of the State University of Medan with the Electrical Engineering Study Program 2023 generation. Alright guys, and on this video, on this occasion, obviously, I will present to us the results of my journal review. The title is Why Kirchhoff's Law of Thermal Radiation is Not Violated. Okay, I made this assessment to fill the assessment from my lecturer, Denny Haryanto Sinaga, SPD MM. Alright guys, without lingering, let's go straight to the video.
Journal identity. Title: Why Kirchhoff's Law of Thermal Radiation has not been violated. Volume 1. Year of Publication 2023. Article title: Direct Observation of the Violation of Kirchhoff's Law of Thermal Radiation. Author: Alexander Baker 1 and Wagai Baker 2. DOI: Publisher: Nature Mechanics. Introduction. The background of the research involves the experimental finding proposed by second business Joe Kang and Edward SPGPA in their study on the violation of Kirchhoff's law of thermal radiation in a non-reciprocal photonic structure. SPGPA especially reported the direct measurements and inequality between the spectral interaction, emissivity, and absorptivity for photonic design that support the direct mode resonance coupled to a magneto-optic material at the cycle's resonance wavelength. However, the experimental data led a comprehensive presentation of the absorptivity and emissivity curves in a single full-size graph with error bars and an uncertainty analysis. This to quantify the statistical significance of the inequality between absorptivity and emissivity. The study by SBGPA raised questions about the validity of the claim of the violation of Kirchhoff's law of thermal radiation, leading to a critical analysis of the experimental findings and their implications. The background of the research involves the need to access the experimental data and claims made by SPGPA regarding the violation of Kirchhoff's law, as well as to evaluate the practical implications of the climate violations. Theoretical or conceptual consideration. The Kirchhoff's law of thermal radiation is a fundamental principle in thermal radiation physics, stating that the observation of radiation by an object at a specific wavelength is proportional to the emission of radiation at the same wavelength. Mathematically, this law can be formulated as the application of Kirchhoff's law to non-replicable photonic structures relates to how the object or structure interacts with thermal radiation. Non-replicable photonic structures can be designed to have specific optical properties, such as directing or relating the flow of photon. Here are some applications of this principle in the context of non-replicable photonic structures. 1. Control of thermal emission. By designing specific photonic structures, you can control the thermal emission of the object. 2. Heating and cooling efficiency. Non-replicable photonic structures can be used to improve the heating or cooling efficiency of an object by optimizing the absorption and emission of thermal radiation at specific wavelengths. 3. Application in photovoltaics. In the context of solar cells or photovoltaics, photonic structures can change the absorption of sunlight and energy conversion efficiency. 4. Heat control in nanomaterials. At the nanometer scale, photonic structures can be employed to control the heat emission from nanomaterials, with significant implications in the development of nanoscale thermal technology. 5. Thermal sensors and detectors. Photonic structures can be applied to the development of highly sensitive thermal sensors and thermal radiation detectors. The application of Kirchhoff's law of thermal radiation to non-replicable photonic structures is part of growing field of research attainment and optimizing energy population and understanding thermal radiation interaction at the nanoscale. Principle of thermal radiation, emissivity, spectral direction, absorptivity, and measurement techniques. 1. Principle of thermal radiation. Definition. Thermal radiation is the process of energy transfer in the form of electromagnetic waves generated by an object with a certain temperature. Stefan Boltzmann radiation law. The total radiant power of an object is proportional to the pore power of its temperature. 2. Emissivity and spectral directional absorptivity. Emissivity is the ability of an object to emit thermal radiation compared to a perfect black body at the same temperature. Varies range from 0 to 1. 2. Spectral directional absorptivity. The ability of an object to absorb radiation at a specific wavelength and direction of incoming radiation depends on wavelength and direction of incoming radiation. And number 3 is measurement techniques for emissivity and absorptivity. Pyrogeometry. Pyrogeometry is measurement of emissivity in laboratories using pyrogeometry allows measurements at various temperatures. Part infrared atau PIR. PIR is pyrogeometry measurement of emissivity at far infrared wavelengths, crucial for application outside the laboratory. Spectroscopy is the measurement of absorptivity in Hall spectroscopy, examining how much a substance absorbs radiation at specific wavelengths. 4. Comparison band method using reference materials. With known spectra to quantifiably measure emissivity and absorptivity. And on the 4 is application of emissivity and absorptivity. Thermal industry. Thermal industry is essential in the design of heat exchangers, ovens, and industrial thermal systems. 2. Infrared heating. Used in heating applications utilizing infrared radiation. 3. Space applications. Influence the performance of equipment and instruments in the outer space environment. Understanding these principles is crucial in the various fields, including thermal engineering, material science, and energy technology. Accurate measurement techniques aid in optimizing the design and efficiency of thermal systems. And then we go to the review of previous research. Then we go to the review of previous research. A finding from previous research relevant to the topic of the journal is that Sihotang visual sejauh fan and actuator from SPGPA reported direct measurements of the inequality between directional spectral emissivity and absorptivity for photonic designs supported guided resonance mode associated with magnetic currents in resonance sample wavelength. However, the study does not comprehensively present the absorptivity and emissivity curves in one full-size graph with error bars and thickness analysis to quantify the significance of the statistical inequality between absorptivity and emissivity. 2. The research methodology used in previous study involved direct measurement of spectral emissivity with a thermal emissions spectroscopy setup measured by SPGPA. While absorptivity was measured with an infrared ellipsometer GA volume, the research also involves applying a tunable magnetic field to the photonic samples to modify the absorptivity and emissivity, as well as active heating of the samples to move the samples out of thermal equilibrium with the laboratory environment.
And now, guys, we go to the identification of research gaps. There is again an exciting research related to previous studies. One aspect that has been underexplored is the need for simultaneous measurement of absorptivity and emissivity in a full-size graph, with error bars and uncertainty analysis to quantify the statistical significance of the inequality between absorptivity and emissivity in the design of photonic structures. Supporting guided mode resonance associated with magneto-optic materials, the resonance wavelength of the sample. Additionally, more research is needed to consider the practical application of the suspected violation of integral and non-replicable photonic structures, especially in the context of thermal radiation-based technology. Rationalization or relevance. The topic is important because it addresses fundamental understanding of thermal radiation and the potential violation of integral and non-replicable photonic structures. This research contributes to the existing knowledge by exploring the direct measurements of inequality between spectral directional emissivity and absorptivity for photonic designs, supporting guided mode resonance coupled to a magneto-optic material. The relevance of this research lies in its potential to challenge established principles in thermal radiation and photonics, which could lead to new insights into the behavior of materials under specific conditions, such as the influence of applied magnetic fields and non-equilibrium states on absorptivity and emissivity. By investigating the direct measurements of absorptivity and emissivity and their potential inequality, this research builds on previous studies that have explored the behavior of materials under different conditions, such as the impact on magnetic fields and non-equilibrium states of thermal radiation properties. The finding from this research could provide valuable insight into the design and application of non-replicable photonic structures for various applications, potentially leading to advancements in thermal management, energy microscopy, and photonic technologies. Overall, the research is relevant in the context of previous studies as
it refers to the direct measurements thermal radiation activities and their potential violation activities of contributing to a deeper understanding of the behavior materials in non-nuclear organic structures, their indication for practical applications. Now we go to the research methods. The previous research detailed direct measurements of spectral, directional, positivity, and objectivity for the photonic designs supporting diagonal resonance coupled to a magneto-optic material. The method involved measuring spectral sensitivity with the home-built engine-operated thermal machine, spectroscopy setup, and observability on the AGA column, required ellipsometer. One application of this method is the direct measurement of acceptability and emissivity, which provides detailed and specific data on the thermal radiation properties of the material. Additionally, the use of short thermal emission spectroscopy and wide ellipsometry allow a comprehensive analysis of the material's behavior under different conditions, contributing to a deeper understanding of external properties. Overall, our methods focus research provide valuable insight into the thermal properties of the material under specific conditions, but its potential limitation in terms of accessibility and resource requirements should be considered when determining its applicability to other research methods. Summary of findings. The main findings of the previous research include the direct measurements of inequality between spectral, directional emissivity, and absorptivity for the photonic design, supporting diagonal resonance coupled to a magneto-optic material. The research observed that the magnetic field had an opposite effect on absorptivity and emissivity at the central resonance wavelength, indicating a potential violation of filtered cloud of thermal regulation under specific conditions. However, it was noted that the law is only valid under steady-state equilibrium conditions. The non-equilibrium state, due to a switchable wide magnetic field, cannot necessarily violate Kirchhoff's law. A specific grant observed was the potential of a non-reciprocal photonic structure to act as a kind of solid-state refrigerant, where the modification of acceptability and emissivity at the switchable magnetic field could allow for entropy. However, it was also argued that further investigation is needed to determine the practical application and performance of this approach compared to the conventional refrigeration technologies. Overall, the research findings suggest the potential for non-replicable photonic structures to exhibit unique thermal properties under specific conditions. But further, studies are required to fully understand implication and practical application of these findings. Implication and recommendations. The findings of the previous research have implication for the field of thermal radiation and photonics. Potential violation of filtered cloud of thermal radiation under specific conditions is non-replicable photonic structures, such as the need for further investigation into the behavior of materials in non-equilibrium states under the influence of wide magnetic fields. This has implication for the design and application of non-replicable photonic structures for application such as thermal management, energy harvesting, and photonic technologies. Based on the findings of previous research, future studies will focus on conducting comprehensive analysis of acceptability and emissivity under various conditions, including different magnetic field strengths and non-equilibrium states. Additionally, our research will aim to quantify the technical significance of the inequality between acceptability and emissivity, potential probe, understanding analysis, and error bars is signal to such gravity. Furthermore, investigating the practical applications and performance of non-practical photonic structures in comparison to conventional application technologies, magnet topologic, photographers, and thermoconductors will be valuable for understanding their potential applications and limitations. In summary, future research should aim to deepen the understanding of thermal properties of non-practical photonic structures under different conditions and explore their practical application in various fields, including thermal management and energy technologies. Alright, now we go to conclusion. The article critically evaluates recent claim the violation of Kirchhoff's law of thermal radiation in a non-replicable photonic structure. The authors argue that the conditions under which the evaluation was claimed do not actually violate the law and suggest that further experiments should be conducted to conclusively demonstrate the violation. They also raise questions about the practical application of the Garnet violation. The main contribution of the article lies in its critical analysis of the climate violation and its call for further research to validate the violation of Kirchhoff's law under specific conditions. Alright guys, thanks for watching this video and next you again on the next talks. See you.